Right. Yeah. Well, welcome everyone. Hello, Ed. Thank you everyone for coming on for another episode of GPU Mode. Today, I'm really thrilled to have like both Jeff Ma and Jay Wan, like two of the co-authors of like, a very new, interesting paper called Cornserve. And what this is it's basically like a system for efficiently serving like any to any models. So, as like many of you have probably played around with like the recent, like, let's say, chat gpt with like their audio models and image models. I suspect these workloads will become more and more important as we like learn how to make LLMs like for text like significantly faster. And so I think it's like the timing is like quite nice to invite Jeff and Jay on. So yeah, thank you folks. Please take it from here.
Hi everyone, my name is Jeff, a second-year PhD student at University of Michigan. Today I will talk about our project Cornserve, and it's a project we've been working on that aims to serve any-to-any models efficiently. So the project is open source at cornserve.ai. Feel free to check it out along with the talk. J1 and I are co-leading project, and while I present, J1 will be in the chat answering some questions if there are any. Right. And I'll get started. So to start with, I will go through the generative AI advancement in history in order to establish our background. So I believe everyone will recognize this. On November 30th, 2022, OpenAI released ChatGPT, an AI chatbot, which is still a very big thing as of today. What's behind it is what we call a large language model, or LM in short. Because ChatGPT models were closed source models, tech companies started to train their own models, seeing the great potential of LMs. So starting in 2023, open source and open-weight models start to catch momentum, signaled by the release of some famous model series, including Llama by Meta and Mistral by Mistral. But how does an LM work? Many of you probably have some sense of it. Essentially, a deep learning model that's trained to predict the next token in the text prompt. When we give an input prompt to an LM, for example, what is Cornserve in this case, this prompt will first be tokenized into 4 tokens and get passed into the LM, which will perform some internal computation and output a token that has the highest probability to be the next token given its training data. In this case, it's. Now this new token will be appended to the original prompt, forming a new prompt. And the LM will simply go on trying to predict the next token. Our LM will keep repeating this process until it hits a length limit or stop token. Then on September 25th, 2023, OpenAI released a new model called GPT-4V, where V stands for vision, meaning this new GPT-4V model can also take images in addition to text as inputs. Later on, we also started to see open source or open-weight models that can take images as input, such as InternVL Chat, Q2VL, and Llama 3.2. We call these models that can take image inputs vision language models, or VLMs in short. But how could these models understand images? What happens is that these VLMs have another small component in addition to the LM we saw earlier. These are called encoders. When both the image and text are provided as input, the text part still gets tokenized into the text tokens, while the image part will go through this new added encoder and produce some image tokens that get merged together with the text tokens. All these tokens together will form the complete LM input, pass into the LM, and thereafter, the LM can continue its business of predicting next token. Because image is a new type of input, we call these input types modalities. And we use a general term for models that could take multiple input types, multimodal input model, or MLMs in short. Of course, there are other modalities, such as video or audio, and the process will be pretty much the same. When there's input video, the video will go through a video encoder, and where there's input audio, the audio will go through an audio encoder. So fast forward a few months, OpenAI released another model called GPT-4o. Here, the O stands for Omni. This GPT-4o model accepts any combination of text, audio, image, and video as input, and generates any combination of text, audio, and image outputs. Well, similarly, we started to see open-weight models that can take multiple input modalities or produce multiple output modalities, such as Yanis Pro from DeepSeek and QN Omni from QN. Given the various input modalities and output modalities of these models, we call these models any-to-any models. How do these models look like? Well, I will use QN 2.5 Omni as an example, which supports text, image, audio, and video as input, and outputs text or audio. As you might have guessed, we have different encoders for different input modalities. And in addition to these encoders and the LM, we have a new component, G. Here stands for generator. For QN 2.5 Omni, this component will generate the audio output. So to give some examples, say we are looking at a request with image and text input asking for text output. This request will only invoke the image encoder and the LM. For a request with video and text input asking for audio output, this will invoke the video encoder, the LM, and the audio generator. Then for a request with video, audio, and text input asking for text output, this will invoke the video encoder, the audio encoder, and the LM. So here we have two observations for these any-to-any models. First, requests have heterogeneities because they may have different input modalities and ask for different output modalities. Second, these any-to-any models are a superset of multimodal input LMs we just saw. So looking at the generative AI model advancement during the last few years, we see the complexity of Gen AI models are continuously growing. Now, I've gone through the model advancement history, which is the first section of this talk. I will then walk through how serving systems evolve with these model advances, which will be the motivation of our project. Then I'll provide a quick overview of our system, including our task abstraction, the planner, and the runtime. And I will dive into them in order. And finally, I will talk about how we implemented Cornserve and share some preliminary evaluations. So recall that an LM is just a function of predicting the next token. It turns out that this generation process can be divided into two phases. The first is prefill, the process of generating the first token, which is generally compute bound. And the other is decode, the process of generating subsequent tokens, which is generally memory bound, as this process will reuse more and more intermediate results called KV cache from previous generations as the output gets longer. One of the state-of-the-art LM inference engine is VLM, and here is how it will handle multiple requests. And here the x-axis is the time. When request 1 arrives, VLM will first start the prefill process of request 1, and then decode until request 2 arrives. Now, VLM will perform the prefill of request 2, and then batch the decode of request 1 and request 2 to improve the system throughput. This will be similar for request 3, where prefill runs first, then VLM will batch the decode of all three requests together. However, from each request point of view, request 1 gets interrupted by the prefill of request 2 and request 3, and request 2 is also interrupted by request 3. To avoid this, people have proposed having dedicated instances for performing prefill and decode separately. This is what we call PD disaggregation in short. Say we have one prefill instance and one decode instance. For the same three requests, when request 1 arrives, the prefill worker will perform its prefill and then transfer the KV cache to the decode worker where decode happens. Now, when request 2 arrives, the decode worker can continue the decode of request 1 and only starts to batch request 1 and request 2 when the prefill of request 2 is completed. This also applies to request 3. Now, moving to MLM serving systems. Recall that MLMs are just LMs with an additional encoder, and these encoders are generally very small compared to LMs in sizes. So what people realized is that they didn't need to modify too much on top of their existing survey engines. For VLM, they just put the encoder together with an LM. I'll denote this the option by monolith. But since there are essentially three parts, or three phases, encoding, prefill, and decode, people also explored how to slice them or put them into different workers. For PD disaggregation, where encoder just lives together with a prefill worker, because encoder only needs to run once before prefill. This option I'll denote it by EP/D. Then there's also the option of only disaggregating the encoder into dedicated workers, or having EPD completely disaggregated into different workers. So all these deployment options are proposed by different people, and somehow, interestingly, they all claim that they are better. But which option is actually better? The answer is it depends. So here we swept these configurations for serving one specific model intern VL3 on 8 A100 GPUs with different input workload and plotted the throughput heat map. The x-axis is the deployment option. 4 monolith means 4 replicas of the monolithic deployment, and 2E/PD means that we have 2 encoder replicas and 3 PD replicas. Note that for this model, because the LM component is too large to fit into one model, we need a tensor parallel degree of 2 for each LM component. So the y-axis are tuple of image resolution with image count, the number of input tokens, and the number of output tokens. We could see that sometimes monolithic is significantly better, while sometimes disaggregating encoder is more beneficial. And also sometimes monolithic deployment, disaggregating encoder, or PD disaggregation are pretty much the same. Then we also conducted the same sweep on a different model, QN 2.5VL. And it turns out that for all these workloads, monolithics are always better. So the observation here is that existing systems for MLM servings are at best point solutions that does not work for all models or all workloads.
So Jeff, I just had a quick comment and a question. Just like I think J1's keyboard is quite loud in the background, just in case, because it'll show up in the recording. Yeah. So then, yeah, maybe just let them know, and I'll ask the other questions.
Gotcha. Cool.
Okay. Yeah. So the question was, so like I would have expected here, like, why is the baseline 4 monoliths? Like, because like everything here, most of the things seem to sum up to 5. Some of them sum up to 4. You know, why 4 monoliths? Why not 5 as the baseline here?
Oh, so as I mentioned, all the experiments are conducted on 8 A100 GPUs, but because the LM component is so large that it requires TP degree of 2, so that you need 2 GPU to run the LM component.
Okay.
So for monolithics, well, each monolithic deployment or replica will use 2 GPUs. That's 4 times 2 equal to 8.
Yes.
And 2 encoders each using 1 GPU plus 3 LM component each using 2 GPUs. That's also 8 GPU.
Oh, so it's 2 plus 3 times 2. I see. Oh, I see. Because the encoder is the only thing that doesn't need the whole model. I see. Okay.
Yeah,
And
because
then, I see.
Yeah.
Yeah, I get it now. Okay. Thank you.
So moving on to serving systems for these any-to-any models, such as QN 2.5 Omni. Recall that these any-to-any models are just a superset of MLMs that has an additional generator component. But unfortunately, this additional component makes it hard to serve these models efficiently. First of all, as the model complexity grows, the difficulty of orchestrating all components within a single engine also grows. More critically, each component has different computation capabilities. So we run each component over a real world trace. and discovered that each of them has drastically different throughput. Here, the audio generator turns out to be the slowest component, and if served within a monolithic server, the system performance will of course be bottlenecked by this audio generator component. So looking at these serving systems and their evolution history compared with the model advancement history, we see that systems adapt after models advance, and existing systems are best solutions for a subset of models under a subset of workload. There are no general solutions for any-to-any models. Well, shortly after we announced Cornserve, VLM Omni showed up, so I cannot claim that there are no existing solutions anymore, but still, there's a gap in existing solutions. Well, the purpose of this talk is Cornserve, I'm happy to discuss VLM Omni at the end of this talk. So here we present Cornserve, an efficient online serving system we built from scratch that natively supports generic any-to-any models. We handle the init heterogeneities of any-to-any models, including request heterogeneity and component heterogeneity through model component level disaggregation. And we will address the model and workload characteristics through component-wise profiling. And in the end, we optimize the total resource usage or serving capacity through disaggregation and co-location planning. So to give the overview of our system, I'll first go through how a model is deployed in Cornserve. First, we have a gateway, which is the entry point for control signals, such as model deployment and inference requests. When a new model is deployed, it starts with a model definition together with its intended serving workload, which will be passed into the planner. The planner will invoke the internal profiler to understand the characteristics of each component and the workload, and then use the solver to plan the resource allocation and the deployment strategy for the model at component level. Once planning is complete, task managers for each model are launched with planned resources, and task managers will spawn the task executors correspondingly. Now, when an inference request arrives, the gateway will produce the component invocations, as not every component might be used for this request. This will be passed into the task dispatcher, which will dispatch each component invocation to its task manager and subsequently task executors. So in general, Cornserve has two large components, the planner marked with the green box and the distributed runtime marked with the purple box. Now the planner here is not yet open source because we're still working on integrating it into the big system, so stay tuned for updates. But notice that both the planner and the runtime rely on the model definition or the model graph, which is worth explaining. I took a screenshot of the model definition of Q13 Omni from Hugging Face. We see that it has submodules like thinker, talker, and code-to-wave. And zooming into the thinker, it further has smaller components such as the audio encoder, the vision encoder, and the LM. We see that there are clear boundaries of these components in model definitions, and as such, we have the task abstraction in Cornserve. So task is essentially a unit of work that is executed in the Cornserve data plane. There are two types of tasks. The first one is the unit task that are the smallest and the most basic type of task. They are executed in a single Kubernetes pod, and they are the smallest unit of scaling. So for instance, they could be the image encoder or the LM. Building on top of these unit tasks, we have composite tasks that are a composition of one or more unit tasks. They are defined by the user in Python, and we have some built-in composite tasks, such as the MLLM composite task and the Omni composite task. To give a quick example, let me show you the MLLM composite task in Cornserve. So this is the high-level definition of our MLLM task. with some expected fields such as model ID, the modality served, and we also have this field called encoder efficient, which determines whether the encoder will be DC aggregated in the data plane. With these fields, the composite task will instantiate corresponding unit tasks as needed, such as encoders for each modality and the LM task. What's nice about this is that you could now build a composite task on top of existing composite tasks. Say we want to compare the Gemma 3 4 billion and the 12 billion variants side by side. You could simply create a new composite task with two MLM composite tasks. This encoder model ID's extra field turns out to be a side benefit of disaggregating encoders, because all variants of Gemma 3 models use the same vision encoder. So in Cornserve, this specific vision encoder is shared by both models in this case. Now, enough of code. Let me explain the Cornserve planner, which we consider as the missing part in existing solutions. Recall that existing systems are at best point solutions for specific models and their specific workloads. Our planner aims to figure out the best deployment option for any model workload combination. Using a tool example of a vision language model, the planner accepts two inputs: the model computation graph defined through our task abstraction, and also the target workload, which includes the request distribution of each request type. For this tool example, let's say we want to minimize the number of GPUs needed to serve this workload. So from the computation graph, the Cornserve planner will create an executor graph. And here, say we have three possible task executors: the disaggregated encoders, disaggregated LMs, and monolithic deployment. Looking at our workload, we have two types of requests: text-only and image and text requests. So the planner will first run a path analysis on each request type. Looking at text-only requests, the planner will search for all possible paths for this request type. And in this case, there are two paths apparently. The first one being using the disaggregated LM, or just use the monolithic deployment. Looking at requests with both image and text, we have three possible paths. The first one is using the monolithic EL, or a request could instead have its image going through the disaggregated encoder. Then here, this request can in fact go to both the disaggregated LM or the monolithic EL. This is because the EL includes the LM component as well. Then all this information will be fed to the Cornserve profiler to profile the serving capacity of each component with each path. And our solver will figure out the optimal deployment plan for this model under this workload, such as how many replicas of each component are needed and which path should a request go through. And this problem is actually formulated as a multi-commodity network design problem. If you're interested, feel free to check out our paper. Now that I've talked about our task abstraction and our planner, I also want to briefly touch how tasks are invoked in Cornserve, since not every component may be used in each request given the heterogeneous modalities, and the system needs to figure out which components are needed. And in this case, we have invocations. So we implemented the record and replay mechanism through a context variable when invoking a unit task. That is, invoking unit tasks in the gateway will only record invocations without actual effects. Then, the task dispatcher will replay these invocations and dispatch them to the data plane. So this mechanism allows Cornserve to only record and replay those needed component invocations, such as the modality encoder for each modality when needed. as such,
I'm
we
sorry, Jeff. I didn't entirely follow this point. Like basically, this is common for people doing like compilery stuff where you'd like to figure like so could you speak a bit more like what do you mean by record here and what are you replaying? Like I'm missing some details, I feel.
so recall here. Uh, so in the purple section is the Cornserve data plane, and a model could have many components. So in this specific example, we are looking at inference request that only invokes the video encoder and the LM component without involving the image encoder.
Mhm.
But if we just run the code directly, the system doesn't really know whether this image encoder is needed or not. It's dependent on the input type.
Okay.
So the gateway will actually first record, basically symbolically execute the code path and realize that only the video encoder and the LM are needed. This process is essentially recording. We executed the code symbolically and only saw video encoder invocations and LM invocations.
And I mean, so like just the simpler baseline here would be like just branching with like if conditions. So like what problem does this solve in addition to that?
I don't think it's solving or comparing with branching. Is really how we implement it as part of the system. It's a design choice.
No, I understand. I'm just trying to understand like what are the constraints that led to that choice, like to because for example, like just to give you a simple example, like if like you have branching and you go like, okay, well, if I have like this kind of image data, then do this, and if I have like text data, then do this instead. Instead, here you're basically recording like a priori like what might happen to do what to spawn like another. This is the part that I'm missing. Yeah.
I see. So that's actually a very good question that's not illustrated by this figure. So particularly say you have a request with both image and audio inputs. These two are not dependent. These two can be executed in parallel. With branching, you have to wait on the previous part to finish until you can look at the next if condition, right?
I see. So basically, because like fundamentally, like I see, like Python isn't like multi-threaded in this fashion, and so you basically separate out like the. So I guess like the way I should think about it is like each of these task managers are receiving like a pipeline of requests. You want to spawn them independently, and then like what the what the executor is basically like it's defined by like a Python file that you then run, but you don't want to run it at initialization. You want to choose like when to invoke that Python file. And this is where this separation helps you. Is that like roughly accurate?
Sort of. We wanted to make these task executors stateless, just like microservices.
All right. Okay. Yeah. Makes sense.
So coming back to here, we implemented Cornserve on top of Kubernetes with approximately 15,000 lines of Python. We built our own custom encoder and generator executors, and we have our LM executor based on MLLM. And of course, we can integrate any LM serving engine such as SGLang or TensorRT LM because of our modular design. And Cornserve can be easily deployed using Kustomize. And we also have built-in observability through open telemetry. Our project is open source at cornserve.ai. So in the end, I want to share some preliminary evaluation results we have. So we conducted our evaluation experiments on two co-located A100 GPUs on AWS, where 8 GPUs in each node are interconnected through NVLink. And the metrics we are interested in is throughput. And we want to answer the following questions. How efficiently does Cornserve serve multimodal output models, such as 2.5 Omni, Qwen3 Omni, and Qwen image. And we evaluated this through a real-world multimodal request dataset containing both image, text, audio, and video input. And we also evaluated Cornserve's ability of finding the best deployment strategy for models with existing solutions. In this case, we look at the models Intern VL3 and Qwen 2.5 VL. And lastly, here we swept a few controlled benchmarks using synthetic datasets. And lastly, we also want to understand how efficient is Cornserve's distributed runtime. Given the interest of time, I will only cover a subset of these experiments, and for more results, feel free to check out our paper. So first, we evaluated Cornserve's ability on serving multimodal output models using Qwen 2.5 Omni, comparing monolithic servers implemented through Hugging Face transformers. For this evaluation, we adopted a real-world multimodal request dataset containing text, images, videos, and audio input called ServeGen, and we make 20% of the requests to have audio outputs. So on the left, you can see that compared to monolithic serving, Cornserve could achieve 3.09x or 3.81x throughput improvement, respectively, using 8 or 16 AA100s. In addition to throughput improvements, we also know that Cornserve provides latency improvements. This can be seen in the CDF on the right. So all these are because monolithic deployments can only run components at a time, meaning whenever one component is running, all other components do not make progress. Additionally, monolithic deployments limit the batching capabilities of each component. Specifically, the LM and audio generator component can significantly benefit from contiguous batching, but they cannot be both achieved within a monolithic deployment. In addition, we are able to run...
Just to be clear, the monolith implementation, this is just using VLM, like basically out of the box on this with their encoders?
So here we are using Hugging Face transformers that we implemented because VLM didn't have multimodal output capabilities.
Oh, I see. Okay. So I got it. So you're benchmarking against yourself, but like with a weaker baseline on the monolith. Okay, got it.
Yes. And in addition, we are able to run Qwen3 Omni on Cornserve, which is not possible in monolithic deployment because of OM error on the GPU side. Moving on to multimodal input models where there are many existing solutions, I'm showing you slides of the workflows we swept on Intern VL3. We conducted a range of controlled benchmarks varying image resolution, the expected image count, the input length, and output length. Here, the number 0.6 means for each request, there's a 60% chance that it includes one image of the given resolution. So for the first two cases, we could see that disaggregation encoder is better. And in this case, our Cornserve planner outputs the optimal deployment strategy as 4 encoder instances with 6 disaggregated LM instances. And for the third case, we see that the monolithic deployment is better. For Cornserve's output deployment strategy is even better. What happens is that in this case, Cornserve's planner outputted the deployment strategy of 4 encoders with 6 monolithic deployments, but we have 67.5% of requests routing to the dedicated encoders. This surprisingly surpassed the existing deployment strategies. For the last case, the monolithic deployment is the best strategy, and Cornserve was able to successfully find it as the optimal solution. So in general, for multimodal input models with various existing deployment strategies, Cornserve's planner can find and match the best deployment or surpass existing deployments. And for multimodal output models without existing support, we see that Cornserve is able to serve these models such as Qwen 2.5 Omni, working with Omni with throughput and latency improvements. Oops. Yeah.
It's kind of interesting looking at this chart. Like the monolith baseline is actually one of the hardest to beat. Like more generally, so it seems like quite robust, basically relative to picking one individual optimization, right?
That's correct, because
Hmm.
here we're only looking at throughput. We have some, I guess, analysis in our paper. So PV aggregation is generally optimized for latency.
I see. Got it.
So coming back to existing serving systems for these any-to-any models, shortly after we announced Cornserve last year on November 30th, VLM released VLM Omni in December. Then, in addition to a project OmniServe released together with their HyperClovaX model, SGLong also has an ongoing RFC about SGLong Omni. While we see any-to-any model serving systems getting tractions, well, we are the first one among them, and we are the only one that tackles the planning problem so far. So in the end, I want to highlight our contributions as follows. We identified any-to-any models as an emerging superset of existing models, but with limited support. This is because of their inherent heterogeneities, and the existing solutions are at best point solutions. Therefore, we built a generalized system that serves generic any-to-any models efficiently with an automated planner that can pick the best deployment strategy. And we open source our project at cornserve.ai. With these, I will conclude, and I'm happy to take questions.
Sweet. Thank you so much, Jeff. I guess, yeah, if folks in chat have any questions, feel free to ask them right now. Otherwise, like I had a quick question around like like basically a lot of these ideas would be like significantly more widespread if they're sort of seen in like other inference frameworks like SGLang or VLM. And so is this like something you guys have thought about? Like what would be like a credible way of like merging these contributions there? Like are there sort of any inherent challenges that make it very difficult to do so?
I think a rising challenge or a difficulty we see with these inference engines is that whenever a new model comes out, there needs to be human engineering to implement these models in serving engines, regardless of VLM or SGLang. And for our project, we wanted to offload that to the existing engineers in VLM and SGLang because we believe these implementations can be reused. So we are able to reuse most of the implementation in SGLang and VLM.
And so like when you talk about like executors specifically, like you had a couple of charts where you mentioned that. Is that like running like if you had like basically a text-based VLM instance, for instance?
Yes, it could be a text generation VLM instance, or it could be simply an encoder server that only performs image embedding or
Oh, I
audio
see, I see.
embedding or something like that. Or it could be a generator server that only generates audio outputs.
Yeah, so you don't need to reinvent the wheel and rewrite page detention and Cornserve or anything like that. Like basically, you just fully rely on VLM for their implementations of these algos.
Yeah, that's our plan. And of
Okay.
course, there will need to be some tweaks, but we were able to reuse a lot of their code base.
And speaking of like maybe one last big question here, which is like what's like it seems like a lot of sort of the technical contributions here were more at the sort of like planning and the scheduling layer. Do you sort of suspect in this field there are like basically in your subfield of multimodality that there's certain like kernels that need to be written that not enough people are paying attention to, or is like an encoder just basically a matrix multiplication and then there's like not much else to be done on that front?
So, based on my experience, encoding or multimodal encoding is generally just compute bound attention. But on the multimodal output side, I think people are making progress in terms of explorations. So, for example, in QN 2.5 Omni, the audio generator is a diffusion-based model.
Oh, interesting.
And
I see.
it was very slow. And when it comes to QN3 Omni, they moved to convolution-based models, which it turns out to be much faster compared to the previous version. So I think this field is still very fast changing, and we sort of can't predict what these big techs are doing. But generally, the multimodal output is getting traction, and people are thinking about how to improving them in terms of throughput and latency, particularly for audio outputs. It's very useful on edge devices, on our mobile devices, or on our laptops. And I think these places are where most likely kernel optimization could come in.
Oh, interesting. So basically, the encoding would happen locally, but then the actual like execution runs like remotely. For instance, you're envisioning these sorts of dual setups.
Yeah, there could be cases where some part of the model is executed remotely, and only say audio generation is executed locally on our device.
I see. Okay, so there's one question from chat from Mao SQR, which is: are the gains over monolith due to continuous batching across modalities?
Mostly but not across modalities, but independently within the modality. So yeah, because basically, oops, I think here, so we haven't yet to compare it with VL and Omni, but they're also comparing to monolithic deployments, in which case there's no contiguous batching for the text part, or there's no contiguous batching in the audio generation part.
All right.
Yeah, there's
yeah. Oh, sorry.
Yeah.
Continue.
So there's like one technical part or point that I omitted, is that these Q and Omni series have two autoregressive components. One is thinker and one is talker, and both of them can benefit from contiguous batching and KV cache management.
Maybe this is my last question. So as far as like benchmarking this stuff goes, like typically for text, like I'd imagine, VLM is often looking at like very large batch sizes, very large sequences, but like I think with things like videos, my understanding is it's not like uncommon to just have batch size 1 if the video is like big enough. So how do you think about like what is sort of like a realistic scenario in which like realistic shapes, realistic kinds of inputs and batch sizes that you looked at in your benchmarks?
So there's actually a real world trace called SurfGen they released. They didn't release the specific dimensions, or I would say the resolution of their multimodal input, but they released sort of the token count, and we were able to reverse engineer it to figure out the image resolution and the video input resolution together with the FPS, number of frames, etc. I would say they have a very high variance, but generally there aren't a lot of video inputs and image inputs.
All right. Well, I think that's it for me. Thank you so much, Jeff, for coming on. Thank you, Jaywon, for answering questions in chat. We'll see everyone next week, and thank you, everyone.
Thank you very much. Thank you.